Hello maths fans, I'm Dr. Tom Crawford, a mathematician at the University of Oxford and the University of Cambridge, and today I'm taking an A-Level statistics exam. This exam comes from the AQA Further Mathematics A-Level course, and this particular test is paper 3 from the year 2023. I have the formula booklet. If you've seen any of my exam videos before, you'll not be surprised to hear that I do not have the correct scientific or graphical calculator. We'll see how that one goes. And I have 2 hours to complete the whole exam, which is out of 50 marks. Let's go. Question 1, let's see what you got. I'm expecting stats, but beyond that, as usual, no idea what's on the syllabus, what to expect. I teach a first year undergraduate course in statistics and a second year undergraduate course in statistics, which I'm sure will completely not help me because this is A-level after all. But anyway, let's go. Multiple choice, it seems. The discrete random variable A takes only the value 0 to 4, cumulative distribution function here. Okay, find the probability that A is exactly equal to 2. So if the cumulative distribution, right, so okay, I know this one then. So cumulative means up to that point. So we know from that table the probability that A is less than or equal to 2 is 0.6, and the only other value it could take is 0, and we know the probability that A is less than or equal to 0 is 0.2, so therefore the probability of being 2, because it can only take those discrete values, the question tells me that, is 0.6 minus 0.2, so the answer there is 0.4, and I would circle that if I were writing on the paper, which, as usual, I'm not. Okay, question 2. First mark in the bag, I hope. The time t days between rain showers in a city in autumn can be modelled by an exponential distribution. Interesting, right. So I'm going to jump into university mode, which I'm not sure is what I'm meant to do, but t is exponential parameter or mean 1.25. Okay, sure. Find the distribution of the number of rain showers per, oh god. Reread the question. The time between rain showers can be modelled by exponential. Find the distribution of the number of rain showers per day. Right, so the time between them is exponential, which makes sense. We often use exponential distributions to model time between events. The example that's coming to my mind that I teach on is to do with the time between earthquakes. Exponential distribution. Right. And we want to know the distribution of the number of rain showers per day. So rain showers per day is not exponential. That's the number of events happening where there's a mean number of events. So given the options are exponential or Poisson, I think that's a Poisson. Now, how on earth do I know what the mean would be? I want to say it's Poisson 0.8 because I don't know why it would be the same. I don't have an expectation it would be the same. Oh, it is 0.8 because it's how many per day. Right, so if there's one, okay, I've got it now. We got there eventually. So there's one rain shower, right, I got it. One rain shower every 1.25 days, right. So that's on average, there's 1 over 1.25. Right, 1 over 1.25 per day, which is 0.8. Right, we got there. So it's a Poisson 0.8. That was a lot of thinking for first mark, question 2. Okay, question 3. The masses of tins of a particular brand of spaghetti are normally distributed. Right, so we're saying, right, so let's just say X belongs to normal distribution, mu grams and 4.1. So mu and 4.1 squared. So you write the normal distribution as your mean and then your variance, which is your standard deviation squared. A random sample of 11 tins has a mean, okay, so that's my sample mean, X bar, right, which is the average value of that sample. So that's 1 over 11 times the sum of the individual values from 1 to 11. That's how you work out your mean, and that's 401.8. 1.8 grams. Okay. Just writing out the question still. Construct a 98% confidence interval for mu, giving your values to 1 decimal place. Right, so this is actually the central limit theorem. No clue if that's what the students taking this would call it or if they're taught it that way. But what we're doing here is saying that x bar minus mu divided by, oh god, what is it? It's sigma over root n. Sigma over root n belongs to normal 0.1. So that's the idea. Now, we know what x bar is, and we can then form a confidence interval. So we want a 98%. So I need a 98% confidence interval. So I'm going to assume it's going to be two-tailed. Sure. So I need to know, I use phi to represent the standard normal. So I need to know the values there, oh god, for a 98% CI. I'll worry about that in a minute, but the point is I think I know how this works. So you say we need the probability that x bar minus mu over sigma root n between two values, let's call them c and d, probability that that is between those two values, we can say is equal to 0.98. And we know C and D because they are the corresponding values for the normal 0.1. So I am going to guess this is now going to be my formula booklet. So I'm going to open that up and have a quick look. What do I get in here? Right, I've got some statistical tables, students' t distribution, don't want that. Normal, come on, give me a normal. Chi-squared, don't want that. Is there not an... Oh, the normal distribution numbers are probably on your calculator, aren't they? Great. Okay, so I'm going to Google that then, aren't I? Right. Because my calculator would tell me this. Normal distribution, it's a normal 0.1, and we want the table. So I want to know these probability values. So my statistical table reliably informs me I need Z to be 2.33 for that 98% confidence interval. So what I'm looking for here is the value then is minus 2.33, because of course it's symmetric, up to 2.33. So I think it's this, minus mu over sigma root n, less than 2.33. So I think we're saying the probability of this is 0.98. So that's my 98% confidence interval. So now you just rearrange that to get mu in the middle. That's the whole idea. So rearranging, what am I actually going to have if I make mu the focus at the center of the inequality? So I'm going to add mu to both sides. So it's, I'm going to flip that. So it's going to be that mu belongs to the interval, which is going to look like x bar minus 2.33 times sigma over root n, and x bar plus that same term. Okay, so that's going to be my confidence interval, I think. So I now just need the values, right? Calculator time again, which obviously I don't have. So sigma is, I've got the values up here, 4.1. Let's just label that. So sigma is 4.1, n is 11, and x bar is, given in the question, isn't it, 401.8. Right, so the confidence interval, I'm just going to leave it as is. The confidence interval, 98% CI for mu, is the values are 401.8, minus 2.33 times 4.1 divided by root 11, and your upper bound is the same thing with a plus, so 401.8 plus 2.33, 4.1 over root 11. So that interval is my confidence interval. If you're enjoying watching my, let's say, mastery of A-level statistics and you'd like to improve your own understanding, then today's sponsor, Simplilearn, is here to help. SkillUp by Simplilearn is a free learning platform that offers self-paced online courses to help you to upskill in the tech domain. The courses cover a range of topics, including generative AI, data science, machine learning, and many more besides. You'll be taught by industry experts, with partner content from Google, Microsoft, and AWS, and you'll receive free certification for the completion of any course. I've heard firsthand myself from many colleagues and collaborators in the tech industry that right now they want people to help them to understand the algorithms that are currently being employed across the sector. So there really is no better way to prepare for your dream job than to sign up for the free courses on offer from SkillUp. Just head to the link below to explore the available courses and embark on your own personal learning journey. Speaking of learning journeys, let's get back and see how I'm getting on with that A-level statistics exam.
Question 4, more normal distribution. I have a feeling this whole exam could be normal distribution if I remember A-level statistics, which I definitely don't, but that is the one thing I'm expecting lots of. And it would appear to be following my prediction. The random variable x has a normal distribution with unknown mean, mu, and unknown variance, right? So t-distribution, right? Wait. Or maybe not. No, it has to be. Yeah. Okay. Cool. Right. Because if we don't know, if you have an unknown mean and an unknown variance, then you use the t-distribution. Students, t-distribution is the one. Right. Do remember that. So, right. So again, x is normal, but now it's mu sigma squared. And we don't know that, but we can make observations. Yes. So we're going to say that x bar, so the sample mean is 101.5. Okay. And give the unbiased estimate, it does indeed, the sample variance, s squared, which is indeed unbiased. Its expected value is equal to the variance. That's what it means to be unbiased. 4.8. Right. So this is sort of, these are estimates for mu and sigma squared based on our data. And we have 8 observations, so n is equal to 8. Okay. The random sample is used to conduct a hypothesis test. All right. Couple of things going on. At the 10% level of significance with the hypotheses of this. Okay. So saying the null, h0, is that mu is 100. And then the alternative is that mu is not 100. So it could be smaller or bigger. So that means two-tailed. Just important to state that early on. If we were looking there to say mu is larger than 100 or smaller than 100, that's be a one-tailed test. It's clearly two-tailed. And it says carried out. All right, try to remember this. So n equals 8 straight away, and the fact that I don't know mu or sigma squared, we're estimating both of them, means we're doing a t-test. So it's the t-distribution, I know that, and it's t7 because it's t of n minus 1. Right, so we have n is 8, you take t of n minus 1. So, I know that. Now I need to look up the appropriate, what are we doing, 10% level. So the appropriate 0.9 interval. So I'm doing t7, it's two-tailed, and I need the 10% test. So I need to look up the two-tailed 0.9, so that's like 0.05 at either end. So, formula booklet. And I think the t-test, if I remember correctly, was actually in this one, wasn't it? So it is, right. So we need to know, we're doing a 10% test, but it's two-tailed. Right, so it's giving me various values. So I think I'm looking for the 0.9, and I think my number of variables is a t7. So do I want 1.415? I think. So I think B is 1.415 for the two-tailed test. Maybe we don't do one-tailed and two-tailed. I'm not sure. I might be overthinking it. But based on the table and what it's giving me, I think that's what I want. So I now have to, I was going to do the confidence interval, it's the same as before. So I'm testing then the probability of this specific, no, I have to work it out, and then that's the value I compare it to. Right. So I want to consider, we consider, oh God, it's x bar minus mu that we're predicting in the test from h0. So mu given h0 is true. And then you divide by, and we're estimating, so it's s over root n. So I think it's this. So it's similar to the confidence interval, but I'm going to work out the actual value of this. Right. So I think then, the thing I'm going to consider there is 101.5 minus 100. So 1.5 divided by s, which is the square root of 4.8, divided by 8. God, so I am going to have to use a calculator for this, by which I mean I'm going to type it into Google. Really should, said this many times, really should get a calculator. We're going to keep doing all these exams. Anyway, so I want to do I want to see the square root. So I want 4.8 divided by 8, which is 0.6. So I have to square root 0.6, right? And that gives me an answer. And then I'm going to do 1.5 divided by answer. Make it a bit bigger, it's going to make it 1.94. So if it's 1.94, that is bigger than the 1.415. So that would mean, let me think, at the 10% level, the data I have obtained from my sample is rarer. That's the idea here. I have obtained something that's quite a rare piece of data. So that suggests that my hypothesis is false. So I think here we can say reject H0 at the 10% level. Is my attempt to the hypothesis test. I'm sure there are many of you doing A-level statistics screaming into the camera right now. Quite probably will be. I'll find out when we look at the mark scheme. But that's how I would do that test. Okay, carrying on with question 5. Okay. A school management team oversees 11 different schools. The school management team allows each student in the school to choose one activity from 11. Okay, I'm going to have to stop writing this down. Lots of numbers. So we've got 11 schools. And then you pick one out of 11 activities. Okay. Sure. The school management team count the number of students in each school choosing each of the activities. They then conduct a chi-squared test for association with the data they have gathered. Fine. Exactly one of the calculated expected frequencies for the chi-squared test is less than 5. What? One of the expected frequencies is less than 5. I have no idea why that helps. I'm assuming here there's going to be a rule that I just don't know. Okay, so one of them is less than 5. Explain why the number of degrees of freedom for the test is 90. All right. So I know the chi-squared distribution, and I know a chi-squared test. The Poisson statistic is often what you would use here. Now, oh man. So, okay, I'm going to start with how I would think about this in a university second-year statistics course. So what I want to say is the number of degrees of freedom, right, is equal to, so there are 11 schools, and that's fine. And then they have to pick one out of 11 activities. But there's a restriction there because the total has to be 1. Right. So I want to say the number of degrees of freedom is, so it's 11 minus 1 times 11 minus 1. So the one I'm so there's 11 degrees of freedom for 11 schools. And then there's 11 degrees of freedom for the 11 activities, right? So that's like rows and columns in your table. but then the total has to be fixed. So there must be, right? That's like, there's a restriction there. So you can't have the variables being anything. Like once you pick 10 of them, the last one is we know it because we know the total number of schools or we know the total number of students. So there's always a restriction there on like the sum of something being a fixed number. So normally it's just the number of rows minus 1 times the number of columns minus 1. So that, according to how I want to do this, so I'm just sort of saying here, total is why I subtract 1. So how I want to do this is to say that that's 10 times 10, right, which is 100. Now that's clearly not the answer because it's telling me to argue why it's 90. So what I think, and this is completely a guess, I'm using the answer the question gives me to try and make an argument, which is a good idea if you don't know what you're doing, as I don't. So I think the point is to say, but since the frequency is small, so I think that's what the question's trying to tell me. It's saying the frequency is small because it's less than 5. We have to combine with another. Combine with another. So I think that means there's an additional restriction on one of those columns. So therefore, I think what I would call n times m is actually 10 times 9, which is 90. That, I think, is what that piece of information is telling me. I'm sure that's just something you're taught, right, in your class by your teacher about you must do something when the frequency is small. It makes sense because it's kind of saying you don't have enough data there to actually for it to be reliable, right? That's the idea. So it's a sensible thing to do. I just feel like there's a rule there that I'm not aware of, but I can argue it and pretend that I knew the rule. All right. Poppy? Convince myself. The school management team claims there is an association between the school a student attends the activity they choose, and they get a test statistic of 124.5. Right, so we're claiming the chi-squared test statistic is 124.5. And then we have to test the claim using the 1% level of significance. Right. So test association at 1% level. So I need a chi-squared distribution with 90 degrees of freedom. So we need the 0.99 value, because it's at 1%, for a chi-squared distribution with 90 degrees of freedom. So I'm going to assume now I look at the table, hopefully. So where is my formula booklet again? It's just lots of looking up formulas so far, this isn't it? Kind of what I remember from making statistics, actually, lots of looking up formulas. Right, so chi-squared down here. Oh, right. Satisfying that appears the random variable having that distribution yet. So we want chi-squared of 90. Right, we've got a chi-squared of 90. At the 0.99 level is 124.116. So P is 124. So we are above that. So I've called it chi-squared. Let's call it chi-squared hat. I don't know what I'm supposed to call that. So the statistic value we have is 124.8 is greater than P. So therefore, the association holds. So therefore, there is an association. That is what the data is telling us. We are again in that very, very, very tail of the distribution because we have a value beyond the 99% interval. Pause C, long one apparently. I'm going to keep going. During the test, the value observed minus expected, O minus E squared over E, was calculated for each group of students. The values for 4 groups are shown in the table below. Oh, okay. State with a reason which of the 4 group students represents the strongest source of association. Okay, so what does strongest source of association mean? Right. So that's the observed minus the expected frequency. But if we assume that they are related or they're not related, Oh, God. Let me read the question before. Claims there is an association between the school and the activity they choose. So this might have affected me in part B. What I'm not sure about is whether my null hypothesis is that the two things are linked, right? Is it H naught that there is an association? And then I'm testing it against alternative hypothesis H1 there isn't. Because that is going to make a difference to what statistic I'm calculating. Right? Because if I'm assuming there is an association, the observed and the expected should be close. And so the small value is in support of H naught. That there is an association. Yeah, so assuming there is an association. But I feel like the larger values here contribute more to the statistic, because the statistic is kind of a sum of these things. And we got a large statistic. So I think, again, I might be misremembering, but I want to say the contributions here depend on what your hypothesis test is. So maybe I should let's go back and actually state clearly a H0 and a H1. And then I'm going to answer the question based on my null hypothesis. That's going to be my idea. I don't know what else I can do because this could go either way. It depends on which hypothesis is which. Okay, so, right. So if I assume H0, so the null, I'm going to assume null means no association, right? So let's say H0, there is no association. And then H1 is there is association. So, so now my hypothesis test, so I assume there wasn't, I got a really big value, which seems to suggest that there is. Yes. So I'm like, if there is no association, I wouldn't have got such a large value. Yeah. Okay. So therefore, what I'm doing here is, I am reject H0 for part B. And what that means now for part C is I want the largest value, right? So I want the largest value. Again, if I'd swap my hypotheses the other way around, I would be flipping it and doing it the other way. But because I don't know, unless I do know, what's the total of all of these bits? Okay, this is not all of them. No, it's just a few of them. Fine. So I'm going to say if I had them all, I could check what the test statistic actually was. Like I could work out how they calculated it, and then I would know what the null and alternative were. Anyway, so I think the largest value is the 1. So that's school 11 and activity 7. So school 11 and activity 7. All right. And I better leave it there because I don't want to spend forever. I'm going to move on to question 6. All right. So 6 got in store for me. A game consists of 2 rounds. The first round of the game, this sounds like a fun game. The first round of the game uses a random number this is a very fun game. Generator to output the score X, a real number between 0 and 10. All right. Find the probability that X is greater than 4. Okay. So, surely, I don't know if I'm supposed to talk about distributions, but we're going to pick a number from 0 up to 10, and we want to know the probability X is greater than 4, then that is surely 0.6. I reckon that's, it's got to be, right? Because if it's random, we're going to assume that these numbers are uniformly distributed. Then that should work. Yeah. All right. Sure. I think. Okay. The second round of the game. Ooh, now we're rolling a dice. This is unbiased dice. With face... Dice or die? It says dice, so I'm going to say dice. With the faces numbered 1 to 6 to give the score Y. The variables X and Y are independent. Yes, I would expect a random number generator is independent of a dice, apparently, roll. Find the mean total score. Whoa, okay. So the expected value of X, let's think about it that way. So the expected value of X, there's no reason to pick one value more than another, so that's just 5. Right, we would just expect on average a value of, well, it could be any of them though, couldn't it? Oh, so you normally would do, all right, let's assume it's integer, I think. Assuming it's integers, because otherwise it really should tell me if they're integers, shouldn't it? So anyway, it doesn't, but let's suppose they're integers, because otherwise I wouldn't have a distribution. So the expected value is just the average. It's a uniform distribution on 1 to 10, or between 0 and 10. Okay, so it's a uniform distribution on 1 to 9. Yes, so uniform distribution, right. So let's just check this. So I'm saying x belongs to, not 0, it says between 1 and 10. So I'm assuming integers must be 2, 3, 4, 5, 6, 7, 8, 9. So the expected value then is going to be the middle value, 5, because it's the two endpoints, 1 plus 9 divided by 2. Right. Good. And the expected value of y is the roll of a die, which has expected value 3.5. If you've ever worked that out, I have. So the mean total score, so therefore the expected value of the total score is x plus y. Because they're independent, well, it doesn't matter if they're independent, in fact. I just add them. Expectation is linear. So that's just 5 plus 3.5, which is 8.5. Okay. Cool. Come with that. Good. That was nice and easy, I think. I always regret saying it's nice and easy, because then I probably got it wrong. Anyway. Okay, so that was B part 1. My bad. Find the variance. Okay, so it's not part C, it's B part 1 and B part 2. So B part 1, I've worked out the expected value, and I want to know the variance. Right, so can I quote variances? That's the question, isn't it? So the variance here is, what's the variance of x? Let's think about it. So the variance of x is, oh god, I see stage value of x minus that, but it's a uniform distribution. So it's something in my head is telling me that it's the endpoint. So it's like b minus a squared divided by 12. Right, where they're the endpoints of what I'm sampling from. Now the question is, do they include 0 or 10? Because I want to say the variance would be, I want to say it's 100 over 12 is what I think the variance is. Now, but then that, because I think this is it doesn't affect my answer earlier, but I think this is going to have to include that, because then the numbers are nicer. So given the distribution of x I have picked, so it's a uniform distribution, the endpoints are 0 and 10, so the expected value is just that divided by 2, a plus b divided by 2. So I'll just write that. Note to self, this is just a plus b over 2. And then the variance for a uniform distribution, b minus a squared over 12. So then it's 100 over 12, which sounds right. Okay. And then I need to know the variance of the dice roll. Oh, I must have worked this out at some point. I probably have, but so rolling the dice. No, wait. I do know this. There's what distribution do we have? So rolling a dice is oh man. It's uniform again, isn't it? It is uniform. Right, yeah, it is uniform. It's just uniform. 1 to 6. Well, it's uniform on the integers, yes. But it's 1 to 6. Right, yeah, because then you add them to get 7 divided by 2. So we can do the same thing, right? So therefore the variance of y, okay, this fills me with more confidence. Variance of y is then 6 minus 1, 5, so 25 over 12. So much smaller, which makes sense because the range is smaller. Gotcha. Yeah, okay, and I do think it's going to be 0 and 10 rather than 1 to 9, because it just says between that. I'm gonna assume between means including the endpoint. Okay, so then the variance is that. So then the variance is of the two things. Variance basically is linear. You have to square the scalar that's there, but there isn't one there, so it's fine. But just for those of you, if you know, you know. It's basically linear, so it's 125 over 12. Is that it? That is it. All right, move on. 7. Company A uses a machine to produce toys. I love the specificity of a machine to produce toys. Number of toys in a week that do not pass the quality checks is modeled by Poisson. Okay, so number of failures. This is classic Poisson distribution territory. Looks like Poisson. And what's the mean? Distribution X with standard deviation 5. Oh god, what my Poisson standard deviation? It's 5. Yeah, it's 5. It's a Poisson 5. So the mean and standard deviation are both lambda, I think. I'm going with it. Maybe it will tell me in my formula booklet. Let's check. I think that's right, but let's see if it's in the formula booklet. Might as well make use of it if I'm allowed. Poisson, yes, mean and variance. Oh no, wait. Glad I checked. Standard deviation 5. So it's not 5, it's 25. Nearly messed that up. Right, because because the variance is lambda, but I've got the standard deviation, which is 5, so it's squared out is 25. Yeah, so I knew that root lambda, right? So i.e. root lambda is 5 because that's standard deviation. Okay, machine producing the toys breaks down. Okay, after it is repaired, 16 do not pass. Okay, so we then have a sample or like a test of that x is then equal to 16, right? So x belongs to this, and then we get a statistic. Investigate whether the average number of toys that do not pass, whether it has changed. Right, I know it's me to using the 5% level. So, hypothesis test, again, like for the 7th time in 7 questions, or it feels that way. Right, so H0, and what am I testing against? Whether it has changed. So the original one is to say that the lambda is 25. And then now my test was x bar was 16, yeah, the average. So then H1 is that it has changed. Now, am I doing a two-tailed or a one-tailed? It says whether it has changed, so I'm going to assume that means two-tailed, which seems odd given it's smaller, but it just says whether or not it's changed. So I'll just say, supposing it means lambda is not 25, so this is two-tailed. Personally, I'd probably do a one-tailed, but it doesn't say investigate whether it is better, i.e. there are less failures. It just says investigate whether it's changed, which to me means do two-tailed. Again, I could be completely misinterpreting the question. That's how I would read it if I was setting this question to my students in my statistics course. Right. So I have to run this test, and I need to compute some stuff. Yeah. So it's just a simple hypothesis test. We know all the stuff, so I can't do normal because it's Poisson. Oh, I have to think about this then now. But I don't know. Oh, am I doing a t-test? So I'm wondering here what type of tests I meant to do. But I wonder if it's just you assume. Okay, so we assume H0 is true and then compute the probability of getting that value. So I think I just calculated Poisson, in fact. So I assume H0 true and compute the probability of getting 16 or fewer. Right? Because I'm looking for an extreme value. Yeah. So the probability of getting less than or equal to 16 for a Poisson with mean 25. So that's going to hopefully be in my table because I do not know. Oh, that's a calculated question, isn't it? Well, let's see. It doesn't seem to want to tell me any of this stuff. It does not want to tell me that. Okay, great. So I'm going to have to look that up. So I need to know for a Poisson, Poisson distribution calculator. Okay, so I'm going to assume my calculator would tell me this if I had one. Obviously, I don't. So the probability of being less than or equal to 16, that that extreme case is 0.03775. 0.03775. So now I'm not sure what to do. I was hoping this was going to solve the problem for me. Because this is less than 0.05, but then that would be for a one-tailed test. So because I'm doing a two-tailed, I think that means that the fact is this is greater than 0.025. So in other words, we're looking at half because it's two-tailed. I'm pretty sure that's how you do it. I've not done a Poisson test like this for a while. So I think you say it's bigger than that, so insufficient evidence. Now, again, if I was doing a one-tailed test, there is sufficient evidence. But I think, again, the way the question's phrased it is to say there has been a change, which means we're doing a two-tailed test, which means you look for half of the probability. So I think insufficient evidence to reject H0 at the 5% level. Again, assuming a two-tailed. If I was going to do a one-tailed, there is enough. But again, I'm pretty sure the question there is wanting me to do two-tailed. Okay, cool. That's a nice 7 marks for that one. Right, and that was part A. So what's part B? Make sure I label that part A. Part B then. For test carried out, state in context the meaning of a type 2 error. So I know this, but I always get these muddled up. Right, so a type 2 error means, oh God, does it mean, so one of them is you accept H0 when it's actually false, and one of them is you reject H0 when it's actually true. So I think type 2 error in the context of this question means rejecting, I think is rejecting H0. No, sorry, means not rejecting H0 when it is in fact false. Yeah, means not rejecting, because that's what we've just done, not rejecting H0 when it is in fact false. I think. Again, I definitely know type 1 and type 2 errors. I teach this to my undergrads. I just always forget which way around they are. So as I just looked at part C, I've reread part B, and it does state in context the meaning of a type 2 error. So what does it mean to not reject H0? So type 2 error means which here, this means that we conclude the, what were we even testing? Conclude the average number that do not pass, conclude that the average number of toys that do not pass quality checks, is unchanged. Yeah, we conclude that it's unchanged because that means we accept H0. Yeah, conclude that it's unchanged when in fact it has changed. Okay. Right, and that's far too much writing for a 1 marker, so that's better be what they want. All right, so lucky I reread the question there, scrolling down the page, because I did not, assuming again that's what it means to put in context. I seem to remember questions like this, they can be quite picky on the marks given about them, so we'll see. Pussy. Company B, the competitor, uses a different machine because they are a competitor, must do things different. The number of toys in a week that do not pass Company B's quality checks is modeled with Poisson mean 18. Great. So why is Poisson 18 now? Which gives me more confidence that I got the first bit right, being 25. X and Y are independent, of course. No reason the two companies have any dependencies. Find the distribution of the total number of toys in a week produced by A and B that do not pass their quality checks. So it's the sum of two Poissons. Okay, so X plus Y, sort of, it doesn't really equal this. I'm going to write it. It's sort of equal to a Poisson 25 plus a Poisson 18. And Poissons, when you add them, you just Yeah, you multiply the two of them together, don't you? Ooh, do you? Do you? Because I think I had the formula for the distribution here. Let's be careful. Let's just check the formula for the distributions of the Poisson. So it's e to the minus lambda x over x factorial. So if I were to add them together, then it would have to be lambda plus mu. Yeah, right? Because you've got that to the power of your lambda x plus mu to lambda naught. I'm pretty sure when you add two Poissons, you just add together their means. Yeah, I think that's right. So I think it's a Poisson 43. Yeah, I'm pretty sure that's how it works. I think it's a 1 marker, so I think that's what they're asking. Okay, right, pod D. Say 2 reasons why a Poisson may not be valid for the number of toys that do not pass. Oh god, the quality checks in a week. God damn it! Right, this is the stuff I was afraid would appear on this exam. Right, there are like, you learn reasons why some distributions are good and bad, and I haven't got a clue. Right, I just know what type of data fits. So Poisson, so like I mentioned before, in fact, exponential models time between events. Poisson is used for like average numbers of things. Like I remember doing it again. One of my questions on the course I teach is number of typos on a page of a book. Poisson. So it is number of toys that do not pass the quality checks in a week. So why is it bad? So I think it's bad because the events might not be independent, right? So I'm going to say that. So I'm going to say reason 1 is failing a quality check. Multiple, let's say multiple toys failing a quality check might not be independent. So for example, and I'm not going to write all this out, I'm explaining to you on the camera. For example, if there's a particular fault, right? If one particular toy has a fault, that could suggest somewhere in the machine there's a problem, and then all future toys will have the same fault. So that wouldn't mean that each individual toy was independent of the others, because they're all coming from the same machine. So it's this independent thing. I think there could be a problem. So multiple toys failing quality check might not be independent events. Independent events. And I just gave my reasoning there about that idea. 2. So what else do we assume for Poisson? We assume that so you definitely need the individual failures to be independent. Fine. So so not independent. What else is bad about Poisson? What else could we possibly say is bad about a Poisson? I'm not sure. Maybe I'll come back to that one and see if I get inspiration. Or is that the end? Oh, that is the end of the question. Okay. So we're producing toys. There could be a problem with the machine that means that a failure is not independent of other failures. That's definitely one of the reasons. Now, what if we don't produce the same number each week? Okay, so we might not produce the same number. There we go. Because, right, demand, Christmas. Produce loads at Christmas, you produce fewer other times of the year. So, yeah, so if you're running the machine more in one particular week, then it doesn't make sense to average. Gotcha. We might not produce the same number of toys each week. Okay. Right, so that's like a difference in demand. That's the first one, is that dependence between the events. Right. Question 8. If I remember correctly, there were only 8 on this exam. So I'm very happy I'm on the last question. And if you really get 2 hours for this, I'm beginning to feel like you probably don't get 2 hours because this has gone way too quickly. Or maybe I just know statistics far too well. I mean, I'm not going to toot my own horn, but we'll see in the marking. Right, I'm going to shut up. We'll see in the marking. Let's just finish. I think this is the last one. Yeah. All right, well, let's finish the exam. Question 8. continuous random variable. Okay. And this is a non-standard one. So what have we got? F of x, continuous random variable, is given by, so I'm going to do some integration here, I'm sure. It's usually what you do on these things. K sine of x, where x is between 0 and pi by 6. Great. And 0 otherwise. Okay. Fabulous. So it's going to look like a bump. Sort of like a normal, but with a sine curve. Show that k is 4. Right, so that is because the total probability must be 1. Right, so the total probability must be 1, and that's going to determine k. So i.e. the cumulative distribution, a probability f of x being less than or equal to pi by 6 must equal 1. So what that means is f of pi by 6, right, i.e. so it's a probability, not f. So i.e. capital F of pi by 6 must equal 1, where capital F of a value is the integral to that value. So the integral of 0 to x, of f of s ds. Right, so I'm going to just integrate. So therefore, we know that 1 must be equal to the integral from 0 to pi by 6. So across the full range of values, the area under the curve has to be 1 because that's the total probability. So that's just k times sine of x dx. So then that's now equal to, oh god, sine, you differentiate cos, you get minus sine. So it's going from minus k cos of x between pi by 6 and 0. So then it's going to be minus k cos of pi by 6, which is cos of 30, which fortunately I do know, plus cos of 0, which is 1. And that has to equal, minus 1 becomes plus 1. It's not plus 1, it's plus k. I was going to say then, that didn't really work. Right. So we know that 1 is equal to k times 1 minus cos of, I'm going to write it as 30 degrees because cos of 30 degrees, you're coming down, but you're coming down slowly. Oh, wait. Cos of pi by 6 is 30 degrees. Cos comes down. So is that not your root 3 over 2? It is. It's your root 3 over 2. But then k isn't 4. Something's gone wrong. Okay. Think again. Right. There was a phew, I wrote the wrong question down. There's a 2. Right. Answering my own question. So if I put 2 in there, Tom. So it's fine as it is. That's a 2. And then when I then divide by 2, because when I differentiate, I pull out 2 and that cancels, yes. So then it's cos of pi by 3, which is 60, which is a half. That's what I was expecting it to be the nice number. But that's now all divided by 2, so I can say 2, right? So that's equivalent to saying that. Multiplying through by the 2. So I get the 2 is equal to that. It's not cos of 30, it's cos of 60, which is a half. Phew. Now it works. I'm glad they told me the answer, otherwise I wouldn't have spotted that terribly obvious mistake. Read the question.
Right, moving on to part B. Find the cumulative distribution function. That is sweet, sweet music to my ears because I basically just did it in doing part A. So the only difference for the full CDF is we integrate to a general point x, as I wrote just up the page there. So f of x is just that, and I already worked that out. So it's just minus k, which is 4, so divided by 2. So minus 2 cos of 2x, shouldn't write it as x, cos of 2, let's call it s, as I did above, between 0 and x. So again, we're integrating to a general point because we want the probability up to that point. That is the definition of cumulative, adding up to that point. So it's just that, which is then going to give me 2 minus 2 cos of 2x. Awesome, because cos of 0, of course, being 1. Right, but then if I'm going to have to state this properly, knowing these mark schemes, so it's 1 if x is greater than pi by 6, and it's 0 if x is smaller than 0, and it's this when we're between those values. Woohoo! Right, is that it? Nope, another page when I was done. Let's see, find the median. Right, so the median is the halfway point. So if I know, we know the distribution, don't we? So I think for the median, you just integrate to get a half. So to integrate to an unknown point such that we have half the probability. So I have to solve a half. Yeah, a half equals 0 to m of my function. Yes, of my lowercase f of s ds. But that, of course, is just f of m minus f of 0. Is that right? Think about that for a minute. Maybe. No, because f of 0 is 0. Yeah, so it's just f of m. Okay, yeah, it's just f of m. Right, that makes sense. That makes sense, right? It's doubting myself. Right, so in other words, I've got half is equal to 2 minus 2 cos of 2 x to m, because that's what I'm trying to solve for. Yes, right, gotcha. So rearranging that, that's going to be 3 over 2 divided by 2, so it's 3/4. Cos of 2m is 3/4. So the answer I want then is m is a half of arc cos 3/4, or cos minus 1 3/4. I could put this in a calculator. It wants you to 3 significant figures. Can't be bothered. That number is exact. That answer is exact. So I can't be penalized, is what I'm saying. And I'm the marker, so it's all fine. Right, let's get moving to part D. Find the mean of x, giving your answer in this peculiar form involving pi's and root 3's. All right, well, I have a feeling I know why it's got the root 3, because we're doing sines and coses of 30, 45, 60. There's always a root 3 over 2. So to find the mean, so mu, the mean, it's just the integral from 0 to pi by 6 over the full range of x times f of x dx. So that's 0 to pi by, this is going to be integration by parts, isn't it? 0 to pi by 6 of 4x times sine of 2x, right? Because my function is 4 sine 2x dx. Yeah, so using integration by parts, and this is now basically a calculus question. This is going to be u. This is dv. So du is 4. V is the integral of sine minus a half cos of 2x. So using the integration by parts formula, that then tells me that the mean is uv, so minus 2 cos of 2x between 0 and pi by 6, minus, and then v du, so it becomes a plus 2 cos of 2x dx, and that's from 0 to pi by 6. Right, so evaluating the limits, that's just going to give me minus, oh god, cos of, oh wait, there's an x. That's nearly made a very silly error there, because I was like, that doesn't make sense. I know I've got to get a pi in the answer. It's going to come from this bracket. So that was silly. So it's minus pi by 3 times cos of pi by 3, which is a half. So that's a half. And then it's plus the integral of that. So that's very helpfully come from sine of 2x between 0. So sine, of course, of 0 is 0. Sine of pi by 3 is sine of 60. There's my root 3 over 2. I knew that was coming, so it's going to be root 3 over 2 minus pi over 6. And they want it in this very specific form of something root 3 minus pi. So it's got to be a sixth, something root 3 minus pi. And that's 3. So A is 6, B is 3. And that, is that it? That is it. End of questions. Everyone's favourite phrase when they've still got time left, at least, to see in an exam. So, as I mentioned before I started question 8, felt like this is going quickly. And I think I'm happy to say it has gone quickly. So, I definitely didn't need the 2 hours. I don't even think I need a lie down. So I'm going to load up the mark scheme and let's just get to it. Right, I've got the mark scheme in front of me, the official one, but of course I will be generous to myself as always, because I don't have a calculator. And of course my work as well. So let's whiz through this and see what we got out of those 50 marks. Hopefully it didn't go so fast that I messed it up, but we'll see, as always. So lots and lots of blah, 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 blah. Right, circle's correct answer, 1 mark. 0.4, right, 1 mark for that. Tick's correct answer, Poisson mean 0.8. Yes. All right, I had to think more about that one than I should, but we got there. Oh, okay, right, 3. Now we get to the interesting stuff. So Z is 2.33, yeah. And so I want, oh God, 401.8, yeah, plus or minus 2.33 times 4.1 over root 11. Okay. I didn't get the numerical answer that they want because, again, I just didn't put it into calculator. My formula is exactly the same, so I'm obviously getting the marks. Okay, 4. It's t-test, wasn't so convinced by this. T7 at 95% is 1.895. Ooh, ha. So, okay, so this should be, what have I done wrong? Because I said it was T7. I think I know. So I've looked up the 0.9 value, haven't I? So if I open my formula booklet here, I have looked up. I wasn't convinced by these 1, 2 tail things throughout, right? And I've come unstuck because I've looked up the 0.9 value of T7 and I actually wanted the 0.95 value. Yeah. Okay, but I think I'm going to still get the same conclusion though, aren't I? I am going to still get the same conclusion. So, okay, so I got T as 1.94. Right, and I get marks for that. I did the correct T statistic, yes. I correctly compared them, and I rejected H0, yes. So, I think I just lose the 1 mark because I broke down the wrong value, but everything else was correct there. So I reckon, again, I'm no expert and I don't want to look up what all of the different letters mean for the marks because I honestly don't care. I've made a slight error and I have done a 1-tailed test when I should have done a 2, but everything else worked. So it's -1 or -2. I'm going to be nice to myself. So there's -1 mark for that. So I'd get 4 out of 5. Again, that's just because I didn't quite realize what I was meant to do. I think I figured it out later. I probably should have gone back and checked when I did once I sort of cottoned onto it later on, but anyway. All right, fine. Fine. First mark down. There's always a couple. Okay, what have we got to do? 2 rows or 2 columns need to be merged. The degrees of freedom is 11 minus 10 times, 11 minus 1 times 10 minus 1. Yeah, cool. I mean, I'm not entirely sure my reasoning is the same as theirs, but I kind of knew what was going on. So H0 is, thank God, H0 is no association. Phew. This was the one where I was saying, depends which way round I am assuming the null hypothesis to be. So clearly there must be, well, I assume there must be a convention, right? And the convention would appear to be, based on this, one question, but based on this, the convention must be the null hypothesis is no association. So it is correct that there is no, and at H1 that there is. Right. And then we get 124.116, because that's our correct chi-squared value. Yes. And so we reject H0. Great. Woo. Like it. Okay. So that means I'm going to have got the right one here. We need the highest value. Yes. Okay, good. So again, that's because it was actually part C that made me realize I had to specify the null and the alternative. Otherwise, I probably wouldn't have bothered and then would have probably lost all the marks on that one. But so thank you, part C, for helping me do part B. Right, 6. Oh God, this number 1 where I wasn't sure what to do. Okay, so it is 0.6, 1 mark. The expected value is indeed 5. Good. and it's 3.5, and we add them. Brilliant. Although it mentions something called a rectangular distribution, I think they mean normal, uniform even. I think, yeah, because it would have a rectangular shape. Maybe it's called rectangular. I would call it a uniform distribution. But anyway, though I guess, depends whether it's discrete or continuous. I'm calling it uniform. Right, variance 100 over 12. Yes. Huh. So I'm saying the variance is... Have I made a silly error here? Oh, maybe I have. I might have made a silly error. I don't think it's b minus a. Okay, so I think it's b squared minus a squared, isn't it? Is that the formula for the variance? Is that what I've done wrong? Because it would work on the first one because it's still 100, but it's messed me up on the second because then the second one would be, because the answer is apparently 35, so it's 36 minus 1, so 35 over 12. Okay. And I can get error carried forward, right? So it's minus 1 for that. But I get, that's okay, error carried forward because I added them together. All right, is that... I'm going to have to look up the formula for the variance now. Maybe it was in the formula booklet, actually. Let's see. Was it in the formula booklet? No. Okay, fine. So what do we reckon it is then? Variance of... I probably misremembered this, haven't I? No, it is b minus a squared. So apparently, the rectangular distribution is different to the uniform. Whoops. Okay, so I've kind of messed that up a bit. Right, fine. Hands up. Obviously, I've used the wrong formula for the variance. So that's on me. I thought it was uniform, but of course I now realize a uniform distribution is continuous. And what we've got here is discrete. So I should have just crunched through and calculated by hand the variance of rolling a die, because I could do that. I just didn't really want to. All right, well, that's another mark down. But, you know, overall, still doing okay. Still doing okay. So where are we going next? Where are you? Mark scheme. Come back. Right. So I lose a mark on that. Right. Poisson distribution stuff. So it is 25. Good. It is unequal. This is where I began to think more carefully about one-tailed versus two-tailed. And whew, I did think about it correctly. So this was, again, I got a clue from part B. So it is bigger than 0.025, and so we reject it. Sorry, insufficient to reject for the two-tailed test, which is what they wanted me to do. Phew. Good. Right, a type 2 error is the number of toys has not changed when it has. So the average number of toys is unchanged when in fact it has. Sweet. And apparently I must mention number of toys to get the marks, which seems ridiculous if you understand what a type 2 error is. Anyway, I did write it because I spotted the question was really hinting. I must represent it, mention it in the context. X plus y, I kind of guessed at that. It is the sum of the Poissons. Good. Okay, limitations. May not be independent, and the number of toys may vary to meet demand. I said both of those things. I had to think a lot about that, actually. So I kind of liked that question because it made me think about the underlying assumptions of the model, which often you just, at least I don't, you're just like, oh, it's this type of data, we just go with that model. But that was, yeah, I'm sure it's the kind of thing you're just taught at school, but I like that one. Good to know I can still think about things. Right, and then the last one. Let's see how we did. So k equals 4 because the probability. Fabulous. Yep, fine with that. Right, CDF, 0, 2 minus 2 cos 2x and 1. Fabulous. Median. Cos 2m is 3/4, and then they've got 3 significant figures, but it'll be that. I was just being lazy. Don't have a calculator. And the mean is a 6th 3 root 3. You bet it's 6th 3 root 3 minus 5. All right, so I think that means, I remember 2 that I dropped, so that means 48 out of 50, which is a solid 96%, and a smiley face. I obviously should have got 100. I should have realized that rolling a dice is not a uniform distribution, it's discrete. That was on me. And what was the other one? Oh, and then the one-tailed versus two-tailed. So I figured that out later. I think hopefully I would have known that if I'd like practiced and known like what values the table is giving you and how you're meant to do these questions. So there's a lesson to be learnt there of not a very, very carefully thinking about the question so you have the right distribution. And also their practice, right? If I'd done loads of past papers, I would know that they're not explicit when you're doing two-tailed versus one-tailed. And then I would know that I would have had to half that value. And then maybe I'd have got my 100. But I am very, very happy. It's been far too long since I did A-level statistics, so I am extremely pleased with 96%. So all that's left is to place the A-level statistics exam on my tier list. Now you can all see the tier list on screen, and you may notice that there is both the A-level maths exam and the A-level further maths exam. Now, the paper I have just sat was paper 3, statistics, from the further maths A-level, which suggests it should be of comparative difficulty to the further maths exam. However, I thought it was much easier. So I definitely want it on the easy side compared to further maths. Now, compared to A-level maths, standard A-level maths, it felt of a similar level to what I remember from that exam. So I'm thinking somewhere around there. Now, of course, this may just be because I am more familiar with statistics concepts. Again, this is a course I teach at both first year and second year undergraduate level at Oxford. So maybe it's just that I know the material enough that it felt relatively straightforward. Perhaps it's much more difficult for an actual A-level student. But this list is based on my experience of sitting the exam, and this felt similar to A-level maths. And I can see on the list, the next one is the Irish Leaving Cert. Now that one has mentally scarred me as to how brutal that was because it was just so long and took forever. So with that in mind, I think this is going to sit between those two. So I think it was a little bit harder than standard A-level maths. Relatively similar, but I'll put it just below that, slightly bit harder than standard A-level maths. Nowhere near as hard as the Irish Leaving Cert, so rest assured, people who were in the comments telling me the Leaving Cert should be way further down. It's moving down, it's moving down. I'm going to put statistics as between A-level maths and the Irish Leaving Cert. So that's it. Statistics Further Maths A-level exam completed. If you've enjoyed watching this, then please do remember to subscribe. And if you have any suggestions of other exams you would like me to try, particularly if they're from your home country, then please do get in touch. You can reach me on all social media at TomRocksMaths, or you can go to my website, tomrocksmaths.com, and just click contact, and that comes straight through to my email inbox. I'll be back soon with more maths fun, and no doubt some more high school maths exams in the not so distant future, given I clearly kind of enjoy them. It's a bit of a love-hate relationship, but fortunately all of you very much seem to enjoy them. So thank you for watching, take care, and keep rocking maths.